Let's start with notes from chapter 2.1. This is a derivative and a tangent line problem. So our goal is to find the formula to calculate the steepness or the slope of all tangent lines to a curve. Okay. Let's start with something that we know. We know how to find the slope of a straight line. Slope is easy as long as we can locate two ordered pairs on a line. We can find slope. We can choose any 2 points on this line because the slope or the rate of change or the steepness will be the same no matter which 2 points we choose. And we know the slope formula is simply change in y over change in x. So the question now is, how can we find the slope or steepness of a curve at a point without the use of a second point? Because slope formula calls for 2 points to find the slope, but if we choose a second point, we won't be able to find the exact slope of point P. The best thing that we can do is choose a close point to point P and get an approximation, but we will not be able to find the exact slope of this tangent line, which is touching only 1 point on this curve. So let's start off with an approximation, right? We know that we can find an approximation if we choose 2 points on this curve, which is some distance away from point P, and we're going to find an approximation. You're going to start off with the approximation, find the slope of this line, and then see if we can adapt this so that we can gain a better approximation to reach towards the slope of this tangent line. Okay, but the question is, if we start off with the slope of the secant line, how can we adapt this formula so that we can create a formula that will only require 1 point for the slope of the tangent line? Okay, so before getting to the formula, let's start off with the approximation of the slope formula. Okay, now what we can do to increase the approximation or to improve the approximation or the slope of the secant line PQ is that we can move point Q closer towards point P. So if you see, as we move point Q closer to point P on the curve, you see the slope of the secant line is going to improve, and is going to look closer and closer to the slope of this tangent line. Okay, so the act of moving this point Q closer towards point P is where limit comes in, or where limit becomes applicable. Limit allows us, the concept of limits allows us to move Q towards point P so that we can adapt our slope formula so that it only requires 1 x value, or 1 point. So let's talk about how we can do that. So here we're going to be assigning point P and point Q in terms of variables x and h. Okay, so let's say point P is some x distance away from the origin, and f of x represents the y value of point P. So here I have point P being x f of x, represented by that point. And then let's say point Q is some horizontal distance away from point P, and we're going to let that horizontal distance be represented by h. So then the x value for the ordered pair for Q is going to be x plus h, and then when we plug x plus h into the function, we're going to get f of x plus h. So we're going to let point Q the point that we're going to eventually move closer towards point P, be represented by x plus h and f of x plus h. Okay. So let's see what this looks like once we put this into slope formula. So slope says y sub 2 minus y sub 1 over x sub 2 minus x sub 1. I'm going to let point P be my first point, x sub 1, y sub 1. And then I'll let point Q be my second point, x sub 2, y sub 2. Then when we plug into our slope formula, we have y sub 2 minus y sub 1 all over x sub 2 minus x sub 1. And if we simplify this, if we combine terms here, the x's will cancel out, leaving us with just h in the denominator. So now what we can do is we're going to let h, we're going to use the constant of limits, okay, to decrease the value of h until it reaches 0. So we're going to move h, decrease the value of h, and as we decrease the value of h, point Q will get closer and closer towards point P. And then eventually, when h turns into 0, point Q will reach point P, and then therefore we will be able to arrive at our goal of only needing an x value, one x value, to find the slope of the tangent line. Okay. So now we're here at the general limit definition for the derivative. The notation that we're going to see is this f prime of x, and this is the notation for our derivative function. And our derivative is simply just a fancy word for slope or steepness of a curve at a single point. Or in other words, the slope of a curve, the slope of the tangent to the curve at a point on the graph. Okay, so think of the derivative as a slope finding formula for a curve function where the slope is ever changing. Okay, so let's look at example 1. Find the general derivative for the function f of x equals x squared. Then write the equation of the line tangent to our function at x equals 1. Okay, let's talk about this, this curve f of x equals x squared. So here we have a parabola, right? And now the slope of this parabola is always changing. However, it is changing according to a pattern that we're going to try and figure out. We're going to try and find the derivative function, which will then be the formula that we can use to find the slope of this ever-changing curve as long as we provide the appropriate x value. If we apply the appropriate x value for the derivative function, in return, the derivative function will return will give us back the slope of the tangent line to the curve. Okay? But first, let's see if we can find the derivative function using our limit definition. So here's our limit definition. First, we're going to be adapting the formula. So f of x plus h means that we're going to take the x in the original function, we're going to take it out. In place of it, we're going to plug in the argument x plus h. So x squared gets replaced with x plus h quantity squared. Okay, minus f of x, so minus the original function. The original function is the x squared, so that's where we put it, all over h. So now we're just going to evaluate this as a limit problem that we've done in the first unit, which is we plug in the target value in for h, and we're going to get x squared minus x squared, which is 0. 0 over 0 is undefined. So indeterminate means that we can continue with the problem, that there's a factor that we can take out. So we're going to expand this x squared plus x plus h quantity squared, leaving us with x squared plus 2xh plus h squared minus x squared. The x squared cancels out. We have a common factor that we can take out, being h, and then the h will cancel out with the denominator, leaving us with 2x plus h. Now we can plug in the remaining h with 0. So now we have 2x plus 0, which is just 2x. So our derivative function is therefore 2x, and 2x is or will be the slope finding formula for this specific curve f of x equals y equals x squared. Okay. Okay, so let's talk about the difference between the original function and the derivative function. So they both provide us information about this curve, y equals x squared, but they are going to provide different sets of information. The f of x equals x squared is simply a height finding formula, or you can think of it as a location finding formula. Any x I plug in to the function, in return it'll tell me the y value. So if I plug in 3, for instance, 3 squared will give me 9, so at 3 the y value is going to be 9. Or if I plug in 1, it'll be 1 squared, which is 1. So this tells us that when x equals 1, the height or the location of the graph has a y value of 1. Okay. So now let's look at f prime of x. So f prime of x also provides information about this curve, but it does not give us the location. Instead, f prime will provide for us the slope of the curve at that point. Okay, f prime is the slope finding formula for our function graph. So if I plug 1 into my derivative function, f prime of 1 will give me 2 times 1, which is 2. And 2 is not the location. 2 is going to tell us that at this x value, 1, the slope of the tangent line to the curve has a steepness or slope of 2. And we can visually see it here. The ordered pair is going to be 1, 1, but the slope at that point is going to have a steepness of 2. Okay. Likewise, if I choose -1, -1 in for the derivative function will give me -2. So the ordered pair at -1 will be -1, 1. However, my slope or my steepness will have will be a value of -2. As you can see here, if you were to draw a tangent line through -1, 1 on this curve, you're going to obviously see it's going to be a negative slope. Okay. Now, finally, if we want to write the tangent line equation, we're just have to put into point slope form. Our ordered pair is 1, 1. Our slope that we found was 2. So then we plug into our slope formula. Y minus y sub 1. Y minus 1 is equal to 2 times x minus 1. We can leave it in point slope form, which is the preferred form, or you can put it into slope intercept. Okay. Example 2, find the equation of a tangent line to our function y equals x squared at x equals -5. So we already have the derivative function, which is 2x. So we can simply find the ordered pair, because if we want to find the tangent line equation, all we need is the ordered pair and the slope. So we plug -5 into the function, -5 in for x will give us 25. So our ordered pair is going to be -5, 25. Now if we want to find the derivative function, which will provide us the slope, we plug -5 into the derivative function. So f prime of 5 is equal to 2 times -5, which will give us -10. So we have our point, we have our slope, and then we simply plug into our point slope form, which will give us y minus 25 is equal to -10 times x plus 5.